everyone. Okay, let's start off by just showing you guys a familiar picture. So here's the complexity classes inside of P. Okay, and now just to kind of remind ourselves of what's going on, in case you're not super into complexity theory or anything. I like circuits, so I'm going to think about these classes as being circuit classes. So NC1, remember, is the class of polynomial-sized formulas. We think of L as being polynomial-sized switching networks or branching programs. NL is like non-deterministic branching programs. NC is polylog depth polynomial-sized circuits, and P is just circuits. Right? So we have these nice circuit characterizations for all these classes within P. And now there's also sort of these other classes, which are really interesting, but maybe aren't studied in like a typical graduate course. So the two that I'm going to be thinking about today are going to be one class called span programs and one class called comparator circuits. So now what's a span program? Well, span programs are defined over a field S. And it's really quite an elegant model. So they were defined back in the 90s. Okay? And a span program is basically just a matrix. Okay? So we start with a matrix A over F. So here's a matrix over any field, I guess. And now we're going to label the rows of the matrix with input literals. Okay? So for instance, literals can be repeated or they can be negated. All right? And now given an assignment to the input literals, we're going to accept if the consistent rows with those, the rows that are consistent with the input, span the all one vector. Okay? So just for an example, if we have the all true assignment, well, the rows that are consistent with this would be these guys, because x3 is false, so we don't include it. And you can see if you sum these rows up, I'm just going to get the all ones vector. So we would accept. Okay? Now, if we had like a different assignment, maybe now we can't use x2, but x3 is false. So now if you sum up the first row and the last row, you can see we still span the all one vector, so we would accept it again. And on the other hand, if everything's false, well, there's no possible way that we could span the all one vector if we just have this last guy, so we reject. Okay? So it's really kind of an elegant model. It was introduced by Karshmer and Vigderson back in 1990. And what's kind of nice about it is that it gives this nice characterization of log space counting classes, like parity L and mod PL and all these, like a bunch of exotic counting classes within P. Now, on the other hand, we also have these comparator circuits. These have been sort of much less well studied. I'm not going to talk about them too much, but if you want to know what they are, just think of them as being like sorting networks. Okay? So, we have like a bunch of wires going left to right. We label the wires with input variables, and the gates essentially sort bits into some increasing order. Okay? So this is now a familiar picture. Okay? So now let me ask you a question. I mean, how many separations do we have? Well, we all know the answer to that, okay. All right. But I claim that this is actually easy to resolve, okay, if we just stick in m's everywhere, if the state of events in a monotone circuit complexity is much, much better than it is in non-monotone circuit complexity. And let's recall that monotone just means I'm not going to allow negated input literals in the circuit model, okay. So here, practically, this looks very successful for complexity theory in general, right? Like we know everything about monotone complexity theory. So we have all these nice separations, sort of historically, beginning with Karshmer and Vigderson, sort of doing the formal connection between communication complexity and monotone formula size. And then there's all these sort of other nice results. So two things that I'd like to highlight is that, in fact, for monotone span programs, we actually can show that they're stronger than monotone P, which is kind of remarkable since the biggest inclusion that we can say is monotone L. And this is still true in the non-monotone world. And basically the reason is that monotone span programs are like a monotone model that get access to non-monotone operations, right? They can do algebra. And this gives them a lot of power. And another result, which is quite recent and very, very impressive, is this separation of monotone NL and monotone L, which is monotone switching networks and monotone directed switching networks. This was done by Aaron Petechin back in 2010, and his proof is very, very hard and very, very nice. Okay, so there's two kind of conspicuous things here. So we don't have any separations for monotone span programs and anything above here. So what do we do know about monotone span programs? Well, here's kind of a partial history. There's quite a long sequence of results here. So the first major paper getting super polynomial lower bounds was by Babai et al. Back in 96. So they proved quasi-polynomial lower bounds against a function in monotone NP. So Anna Gal used sort of cleaned up and formalized these results using something that we'll call the rank measure, but still quasi-polynomial for NP. And we can improve this NP lower bound, but it goes down to a non-monotone NC. So there's a monotone function in NC which can be computed by non-monotone circuits, not monotone circuits, but which requires quasi-polynomial monotone span program size. So this should be taken kind of as a hint that maybe we should expect that monotone span programs could actually be separated from classes within monotone P, even though we know that they're really powerful in some weird way. And if you'd like extra motivation, I mean, the thing that you can say about monotone circuit complexity is that it's not representative of algorithms, right? Like this, in some sense, they're not interesting. Why should we care about them? So for monotone span programs, there's a very good reason to care about them, and that's because they're equivalent to secret sharing schemes, or at least a big subclass of secret sharing schemes. So if you know what a secret sharing scheme is, I mean, if not, let me remind you, it's just the following cryptographic task where you want to, I have a group of people, and I want to reveal some secret to certain subsets of them, right? And I want the other ones to not be able to get any information at all, okay? So to do this, I'm going to give little pieces of information to each of them, and the groups that I like should be able to recombine their secrets in order to get what I want to tell them. And monotone span program size is equivalent to linear secret sharing scheme size. So there's a natural way to sort of go back and forth between the amount of information you need to share in a linear secret sharing scheme and a monotone span program computing a related function. Okay, so on the other hand, for monotone comparator circuits, well, we basically know nothing. We have exponential lower bounds for clique. That's just because it's a circuit, right? That follows from Razborov's work in the 80s. But we can't even prove it contains monotone NL or monotone L. And this is kind of surprising because we know that comparator circuits contain NL in the non-monotone world, right? So something weird is happening here. So this sort of suggests two natural questions, right? So first of all, can we separate monotone span programs from monotone P, L, over any field, right? And for comparator circuits, same questions, monotone P, monotone NL. And I'm happy to say that the answer is actually yes, and in the progress of doing that, we can basically unify all the lower bounds within monotone P with one technique. Okay, so how do we do that? Well, let me talk about the rank measure. So this is a complexity measure that was introduced by Razborov. So what is it? Well, let's first fix a monotone Boolean function. So let's remember that just means if I take an input to the function and I flip a bit from 0 to 1, that can't flip the output from 1 to 0. So it's monotone with respect to increasing bit strings, right? Okay. So we're going to have some matrix associated with F. I'm going to label the rows with 1s of F and the columns with 0s of F. And this is just an arbitrary matrix. Don't conflate this with the communication matrix or something. It's just some matrix over some field. Okay? So now for each input variable, you can take the submatrix of A just by taking all the 1s where the ith bit is 1 and all the 0s where the ith bit is 0. Right? So it just looks like that. This is going to give us a subset of the 1s and a subset of 0s, and this just gives us a little submatrix. And, if you think about it for a second, as you range over all the inputs, you're eventually going to cover the whole matrix, right? And this is just because the function is monotone. If I have a 1 of the function and a 0 of the function, there's got to exist a place where there's a 1 and 1, where there's a bit set to 1 in the 1 of the function and 0 in the 0 of the function. Because otherwise I could flip it and flip the function from 1 to 0. Okay. So now we can define this rank measure. Well, the rank measure for F with respect to A, so we get to choose A, is just the rank of A over the maximum rank of any of these little submatrices. Okay? So you should think of it like this. If we want to prove lower bounds, on this measure for F, we get to vary A. Choose an A where the rank of A is really, really big, and the rank of all these submatrices is really, really small. Okay? So this is kind of a weird measure, right? At first glance, I mean, this is probably not the first thing you'd think of, but it has a bunch of really remarkable properties. So when it was first introduced, Razborov showed that the rank measure for any matrix and for any field, in fact, lower bounds formula size. And sort of a set of subsequent works shows that you can actually show that it basically lower bounds a lot of the classes within monotone P. So it lower bounds span program size over the field in particular, also switching network size. And we were able to show that it also lower bounds monotone comparator circuit size. This gives us kind of a nice motivation to actually prove lower bounds for it. But now, of course, what's the catch? Well, the catch is that the best prior lower bounds are quasi-polynomial for a function in NP. These are more or less the strongest lower bounds that are known. Okay, so can we improve the state of the affairs? Well, that's our main result. So we can show that there's a function in monotone P such that for some real matrix A, some magical matrix, the rank measure for F with respect to A is exponential in the number of input variables. And similarly, for monotone NL, if you just take ST connectivity, we can find a matrix for which the lower bound is quasi-polynomial. So for prior lower bounds, I mean, this more or less unifies all the proofs for lower bounds within monotone P. So we can also separate the NC hierarchy by simple tweaking of the techniques. We get a simplification of monotone L versus monotone NL, which is really quite nice because that paper is really difficult. It's very, very nice work, but it's quite difficult. And we also get good lower bounds for span programs, like really strong exponential lower bounds for span programs within monotone P and quasi-polynomial for monotone L. And in particular, this gives the first exponential lower bounds for monotone span programs, and therefore the first exponential lower bounds for secret sharing schemes. It's sort of a long-standing open problem in that world. And also, along the way, we can separate non-monotone span programs from monotone span programs, as long as you blur your eyes and don't look at what the field is. Okay. So for comparator circuits, we basically get the same set of results. You know, the first exponential lower bounds for comparator circuits within monotone P, first separations between comparator circuits in P and NL. And this is actually quite interesting because we know that non-monotone comparator circuits can compute everything in NL, right? So this is a non-monotone monotone separation, which is good to know, I guess. Yeah. All right, so let's pause for a second, take a breath. Okay, so and let's talk about the proof. Okay, so how does the proof go? Well, okay, so how does the previous proofs go? Maybe that's the more important question. Maybe that's the question that you guys care about. Well, the previous proofs, remember that what we want to do is we want to construct this magic matrix A somehow for the functions that we want to lower bound. So the previous proofs, they were very direct, and they're sort of combinatorial, this very combinatorial flavor, and more or less they had this method of constructing a matrix combinatorially, and then a way of converting that matrix into a function, and that function was in NP. Yeah. And sort of one of the things that kind of limits this approach is that the resulting matrices have 0, 1 entries, and more or less by communication complexity arguments, you can get quasi-polynomial upper bounds in this kind of case. So we know that this isn't going to work. So in contrast, we're going to do something which has been a pretty common theme in the past couple of years, and certainly a common theme at this conference. We prove a lifting theorem. So what we do is we reduce the problem of constructing A to lower bounding some new algebraic measure that we call the gap complexity or whatever. Okay? And kind of the key thing is that the matrices that get spat out by our lifting theorem, well, they just have really arbitrary real entries. So they completely avoid this quasi-polynomial barrier. Okay. So let's, in the time that I have left, maybe I'll talk about the proof in a little bit more detail. So here's this funky measure. Okay. So we want to come up with a way of constructing this special matrix. So the first thing to do is to say, well, we know that with certain special functions, f, we can associate a very natural search problem. Okay? Don't worry about how to do this. This is kind of well known in the literature. For people in the know, I mean, for Gen, we get like pebbling-like problems, and for ST connectivity, we get problems like the fork game, things like that, right? And now, what we're going to do is we're going to reduce constructing the matrix A to just lower bounding a complexity measure on this search problem instead. Okay. And then finally, we actually prove the lower bound on the search problem. Right? So it's really simple in 3 easy steps, I guess. So now the first step is basically done. I mean, this follows from earlier work, Ross and McKenzie, and sort of cleaned up and sort of enunciated in Gusa Patassi, and also many works in this conference that I've forgotten to cite. So for instance, the nice proof complexity paper we saw earlier. So let me just say a few words about the second 2 steps. So we're going to focus on the search problem associated with that. And we can there's a natural way to associate it. All right. So how do we do this? So what are these lifting theorems? Let's first talk about them in the communication setting. This is kind of the classic setting. Okay. So we have some search problem. Okay. So you get some Boolean string as input, and you want to output some thing that's related to it in our search problem. Okay. So ideally, the search problem starts off, and it's hard for some weak complexity measure. Okay. And what we would like to do is we would like to convert it into a function that's hard for communication complexity. So what's the natural way to do that? Well, we need to somehow give inputs to 2 parties, right? So I'm just going to kind of do it arbitrarily. I'm going to literally choose a domain for Alice and Bob, okay? And I'm going to just compose the elements of the domain kind of arbitrarily together to get this to get some input to the search problem, right? So we choose some function g. It takes one of Alice's inputs and one of Bob's inputs. It outputs a string, or just a bit, and we just plug that into the search problem. So to solve this new problem, all Alice and Bob have to do is evaluate g on all of the coordinates, and then solve the search problem on the string z that gets spat out. Right? And if you choose g correctly, well, the resulting thing is going to be hard for the strong complexity measure. In this case, it's like communication complexity. So basically, the best thing that Alice and Bob can do is evaluate each coordinate bit by bit and simulate the decision tree, kind of the intuition here. So now what happens in our setting instead? Well, we're in kind of a funny situation, right? Because so just from the outset, we have a search problem. Okay, we know what the hard complexity measure is. It's this weird matrix thing. But we don't know what the weak complexity measure is, and we don't know how to lift the thing we don't know that it exists. Right? This is, intractable. So the observation is that this matrix A has to have values taken from some field. So before we composed it with the search problem directly. So what we're going to do instead is we're going to introduce some indirection. We're going to introduce a polynomial which certifies what we're going to call a large algebraic gap for the search problem. And instead of composing our gadget from before, our little inputs from before, with the search problem, we'll just compose it with the polynomial instead. And then just by running, running this thing over all the ones and the zeros and just plugging it into the polynomial, we'll get the entries for every guy in A. So kind of the main lifting theorem here is that, if we consider layered ST connectivity on the m squared by m grid, just for the sake of ST connectivity, our true theorem is a bit more general than this, and we let K be this algebraic gap complexity, whatever that means, then you can show that the rank measure is more or less lower bounded by m to the k, so m to the gap, right? And the proof is more or less you just use the intuition on the previous slide, and we have to do a little bit of an extension to the pattern matrix method, but let's not worry about that. Okay, cool. So now we know that the rank measure is something like n to the gap of f. So all we have to do now is prove a lower bound on the gap. So to prove a lower bound on this gap, I have to tell you what the gap is. Well, first I'll tell you what the search problems that we're going to be looking at look like. Okay? So we start with an unsatisfiable CNF. Okay? And search CNF is just the following problem. You get an assignment to the variables of f, and you output the name of a clause that's falsified. Okay? All of our search func problems that get associated with functions are of this form. Okay? And now, what's an algebraic gap? Well, if you start with one of these search problems, then the algebraic gap complexity of the search problem is just the maximum k for which there is a polynomial with high degree, like degree n, but for each certificate of the search problem, so for each assignment which falsifies one of the clauses, if I hit the polynomial with that restriction, the degree is going to drop like precipitously. Like it's going to, somehow the polynomial is big and complicated, and if I hit it with a restriction, it suddenly simplifies a lot. So now, if you take like the OR function, for example, and look at its Fourier expansion, that kind of satisfies exactly this. But the thing that's weird there is that it's not total. Like the OR function has a bunch of very small certificates that fix bits and simplify it to a degree 0 polynomial. But not every restriction is going to contain one of those. So we really want it to be total. So I don't really have time to tell you how we get the algebraic gaps, because it's not an easy problem. It involves sort of looking at big systems of linear equations and reducing them. But maybe I'll just say, to get a lower bound for ST connectivity and for gen, we more or less reduce to something called reversible pebbling, or this Diamond-Tompa pebbling game, if you're familiar with it in that form. So we can show, say, for ST connectivity, you can always, the right gap, so there is a polynomial for which the gap is log n, and in fact, that's the best you can do. And for gen, if you start with a graph with high reversible pebbling number, then the gap is going to be exactly the pebbling number. And the nice thing is that for gen, we can actually get graphs with like basically linear reversible pebbling. So this gives us our exponential lower bound. Okay, so so now this sort of more or less completes the proof. For ST connectivity, we know that the gap is going to be log n. Okay, so we just plug it in there, and there's our quasi-polynomial lower bound. Okay, all right. So let's just a couple concluding words. I'd like to just sort of talk about some nice open problems. So kind of the main message of our paper is that we can more or less unify all the lower bounds against monotone P by these nice lifting techniques. And along the way, we introduced this new algebraic complexity measure, which is really sort of nice and gets us lots of nice results. So there's an obvious question is whether or not there's more applications for these algebraic gaps, right? We'd love to see, we had this new query complexity measure. It's never appeared before. We'd love to see it being used elsewhere. Average case lower bounds is an obvious problem. That's just, I mean, the rank measure is somehow inherently a worst case measure. So you're going to need really new ideas to get average case lower bounds. And of course, obviously, the question that if you go to any lifting talk is sharpen the lifting theorems further. We want a constant size gadget. That's the main message from the lifting theorem from the people who work on these kind of things. If you get a constant size gadget, then maybe we can get truly exponential lower bounds, like 2 to the n. And finally, I'd like to say this algebraic gap complexity, it's a query complexity measure that's algebraic, but for a search problem. And I don't know of any more of those. All the query complexity measures I know for search problems are like decision tree complexity or certificate complexity. None of them are really algebraic like what we have. No one really ever introduces a weird polynomial anywhere or something like that. So is there any, is there a theory lurking there that just hasn't been discovered yet? And is this just the first step? I'd really like to know the answer for that. Right. And thanks for listening. Oh, I see, yeah, okay. So the question is, we also know lower bounds, say by communication complexity, that get lower bounds for clique, and depth lower bounds, say for NC1. Yeah, sure, yeah. So the clique lower bounds for depth in particular don't, I guess the major problem is that I don't know how to represent clique as a composed function. So that's basically where this whole thing kind of shuts down. Whenever you have a function that's not a composed function, the best you can basically do is by a reduction. So you could certainly reduce, say, gen to clique, and you'd get lower bounds from that. So our proof technique works with respect to reductions. In fact, we can get lower bounds for like bipartite matching by doing that for monotone span programs, just by doing a reduction from ST connectivity. But yeah, and the size question, I mean, we'd love to have. I mean, I'm not sure if that's your question, but we'd love to have a lifting theorem for size, but that seems like a really hard problem. Some fusion technique or something.